Good morning. This is lecture 3, unit 2, RFIC design. So in the previous class, we were looking at noise figure calculation basically. So noise figure is, just to review what are things we have done in the previous class, noise figure is defined as a ratio of the signal to noise ratio at the input to the signal to noise ratio at the output. And it's a common thing to represent a noisy element as a noiseless element and in series or parallel with the equivalent source. So if it is a resistance, usually we'll represent it as a noiseless resistor in series with a voltage source Vn square bar. And the same goes with any system also, because LNA is the first active block in a transceiver chain, and LNA also add noise to the system, but the amount of noise added to the system is less. Now that LNA can be represented as a noiseless LNA in series with the voltage source. That is what we have done here. Now, based on that, we have arrived at the expression for noise figure. One in two ways we represented. One is in terms of 1 plus Vn square bar divided by 4 kTRS into alpha square AV square. Other one is by just representing the total output noise. We have written in this form as well. And based on that, we have solved one or two numericals to calculate the noise figure. Right. So today we will continue the same, and we will extend this calculation of noise figure to a cascaded stage. So we know that in a receiver chain it is very important. It is very common that in a receiver chain there will be number of stages in cascade. So we should also know how to calculate the noise figure when you have multiple stages in cascade. So today we will discuss about noise figure of cascaded stages. Right. Yeah. So with the intro that a receiver chain will have multiple stages. We are not considering some 3 or 10 stages now. We will be considering only 2 stages, and we'll see how the noise figure of 2 stages in cascade will be. And based on that, we'll arrive at a generalized formula for any number of stages. That is the idea. So in a receiver chain, it is very common that there will be multiple stages. So there will be many stages. And we will be considering 2 stages for our calculation now. So I'm considering 2 gain stages. One is this. So this stage, from input to output, this stage is providing a gain of say AV1. Now, as I mentioned before, the stage is represented as a noiseless stage, but the noise of this stage is represented as the output noise here, and we mark it as Vn1 square bar. This is for the first stage. Now, for this stage, mm, we consider the input and output resistances as well. We are considering it as a voltage amplifier. So at the input side, you will have resistance Rin1, and at the output side, you will have resistance of Rout1. These are the two. We are considering the loading effects as well. This is for this particular stage. Now, to this stage, I am connecting an input. So input is coming from a source, say Vin, and this is the resistance of the input source. So I mark it as Rs. Right. So this is the stage 1. What I have marked inside this dotted box is our stage 1. So similarly, one more stage I will consider. So that will be next stage. That also is I am considering a gain stage there as well. So it is AV2. Now this stage also is treated as noiseless by considering the noise of this stage at the output as Vn2 square bar. Now For this, the input impedance is R in 2 and the output impedance is treated as R out 2. So this forms your stage 2. So this can be marked as stage 2. If there is any background noise from my side, please let me know. So this is your stage 2. Right, and this is the final output. So this is V out. So now what we are going to do here is, there are two stages in cascade, and the source is V in with a source resistance of Rs. So we are going to calculate the noise figure. So noise figure, we know it is a measure of the degradation of signal to noise ratio as a signal travels from one stage to another stage or from input to output. So we are going to find the noise figure of this cascaded stage. That is the aim. We have two stages, and we understood that each stage is providing, so from input to output this stage is providing a gain of AV1, and from here the input to output this stage is providing a gain of AV2, right? So what we will do first is, we know that already we have derived the noise figure expression for a single stage. So from that calculations we know that noise figure can be represented as, noise figure NF can be represented as 1 plus Vn square bar divided by alpha square AV square Vn Rs square bar. Remember, this is the way we represented noise figure in the previous class. So it is 1 plus 1 plus Vn square bar divided by alpha square AV square into Vn Rs square, or this is also written as 1 plus Vn square bar divided by, this can be combinedly, we can write it as A naught square, alpha AV can be written as A naught, and the other one can be written as 4 kT into Rs, because that is the noise resistance, the resistance of the, sorry, the noise of the resistance, the source resistance Rs. This is how we represented noise figure, right? So we will use the same. So what is this Vn square when we can? So this is for a single stage. This we have actually already obtained this for a single stage. Yeah. So Vn square can be, so Vn square is nothing but output noise of one stage. So if since we have done this derivation for a single stage, this Vn square itself is the output noise for one stage, right? Now, so if you look at this cascaded system, first we need to find what is, so what I'm going to do now is I'm extending this formula, or extending this noise figure formula for two stages. That is what I'm going to do. So that means in this formula, I need to recalculate what is Vn square. So Vn square is the output noise of one stage. So I need to find what is output noise here. That is first step. And the second step is I need to find what is A naught square. So what is the total gain or attenuation, the combination of gain and attenuation from input to output. These two things I need to evaluate separately. So let me start with that. So I will write A naught as A naught A naught can be written as V out by V in. So V out and V in are marked here. This is the V out point and this is the V in point. So we are finding V out by V in, the total gain of the system, including all the loading effects within this. So this can be written as, so you can see that there are two stages here. AV1 and AV2 are the gain provided by the two stages individually. Apart from that, when the signal, this signal, when this signal travels here, when the signal travels through this path, you can see that there is an input impedance here. So I told before itself, I am considering this as a voltage amplifier. So the model will be something like this. The model will be like a resistance. Is there any background noise from my side? Can I get some response?
No, sir. No, sir.
All right. Okay. Yeah. Fine. Okay. So this is what this will be the model what we'll be considering. So input impedance will be like this, and R out will be in this form. Right. So we can see that the input voltage, what will be available here at the input will be attenuated by the combination of R in 1 and Rs. So I'll have an attenuation factor here, which is R in 1 divided by Rs plus R in 1. Secondly, again, from the first stage to the second stage will have an input impedance of R in 2, and the output impedance here is R out 1. So there also we will have the similar attenuation of R in 2 divided by R out 1 plus R in 2. So by considering all those things, I can write A naught. A naught is the voltage gain, V out by V in as AV1 into AV2. So AV1 into AV2, those are the two voltage gains of the individual stages, multiplied by the attenuation factors R in 1 divided by R in 1 plus Rs for the first stage into R in 2 divided by R in 2 plus R out 1. So this can be considered as the total A naught. So we have considered the loading effect also in this case. Right. So what I mentioned is, probably if you have forgot what we have done in the previous class, this was the noise figure formula what we obtained, and now I am applying the same noise figure formula for cascaded stages. For that I am finding A naught. I obtained the value of A naught now. Now I need to find what is the output noise of the stage, the output noise of the two stages together. So that means I need to write what is Vn out here. That is output noise, right? So output noise can be represented as, if you look at the system, if you look at the figure here, output noise directly you have some Vn2 square. That is one component of output noise. Along with that, you will have this noise component also multiplied by the attenuation or the gain factors throughout the chain, and that is also available here. Those are the two noise components available. One, the Vn square component, and another one will be the Vn square component travel through the system, and second will be the Vn2 square component of the second stage itself. Right. So I can write Vn out square as, there are two components. One is Vn2 square, that is directly there at the output, Vn2 square. And then the second one is Vn1 square, which is at the output of first stage, which is attenuated by the impedances at the input of second stage. So that is R in 2 plus R out 1, the whole square. Again, that is multiplied by AV2 square. Right. So this is Vn out square bar. So I will mark this as there are two components. There are two components. One is the noise of second stage itself. The second is noise of first stage attenuated and amplified. Right. So after writing Vn out and A naught, what we can do is, therefore now we can write the overall noise figure. So overall noise figure of these two stages together can be written as NF total. So what I will do is, it can be written as 1 plus Vn out square bar divided by A naught square into 1 by 4 kT Rs. The same formula I have written what is the Vn square bar at the output. So output, you have directly the output noise of the second stage plus the noise of the first stage attenuated and amplified by the second stage, and denominator you have the entire gain of the system. So the same thing, if I plug in here whatever formula, whatever things I obtain, I can write this NF total as 1 plus the Vn out square by A naught square. So what you have to do is, you have to put this equation Vn out square over here, then you will get two components there. So let me write it as Vn1 square bar. You also can try along with me. So Vn out is having two components, right? So Vn out square is having two components. One is Vn2 square. So that will have the entire A naught square and 4 kT Rs with that. but along with Vn1 square bar, you have to cancel this AV2 square and Rn2 by Rn1 plus R out 1 the whole square term, because the A naught in the denominator, is basically this. So you have to plug in this over there and then cancel the term. So for Vn1 square, I will write the remaining terms divided by, we will have the Rn1 by Rn1 plus Rs term from the input side, that will be there. Then AV1 square will be there, and this 1 by 4 KTRS will be there. This is 1. And for the second stage, you will have all the components Vn2 square divided by Rn2 divided by Rn1. Sorry, you will have all the components. So we have Rn1 divided by Rn1 plus Rs the whole square into AV1 square into Rn2 divided by Rn2 plus R out 1 the whole square into AV2 square. The entire thing again multiplied by the noise resistance 1 by 4 kT into Rs. Right. So this will be the overall noise figure. So can you guys check this and let me know whether I missed any term? Is this clear what I am explaining? Can I get response in the chat box? So others are not there. Can you repeat which expression? A naught expression 1. Sure, Akshay, I'll do that. Okay, so what is A naught expression? A naught is the total gain provided by the system. So V out by V in. So V out is here, V out is here, and V in is this side, right? So you have two stages directly providing gain, AV1 and AV2, that I have written here directly, AV1 into AV2. Then if you look at this signal source, it will undergo certain attenuation because you have a series RS component here and the input impedance of this amplifier, that is R in 1. So here you have a divider network, so that will basically attenuate your signal. So the signal coming at the input of AV1 is attenuated by R in 1 by Rs plus R in 1. That is the one factor what I have written here, R in 1 by R in 1 plus Rs. Now for the second stage, again what you have is input impedance is R in 2 and the output impedance of the previous stage is R out 1. So that also will be attenuated. So that is the two stages what I have here. Okay, the Rs of the first stage will be the R out of first stage. I didn't get that, Sagar.
So for the second stage, won't the input the RS is considered as the input impedance for first stage, right,
Yes,
sir?
yes.
Then so for the second stage, won't it be the R out of the first stage, sir?
Can you repeat? RS for the second stage be R out of first stage.
For
So yeah, your question is whether this RS R out 1 will act as the RS similar in the first stage. That is a question, right? Yeah, that
yes,
is
sir.
true. That in that way only we have taken it. Yes. RS for the second stage is R out. Yeah, yes,
Okay,
that is
yes,
correct.
sir.
Yes. Okay, yeah.
Okay, got it, sir.
Akshay, is that clear? I explained it. Okay, yeah. Thank you, Akshay, for the response. Yeah, so this is the noise figure expression. But by looking at the expression, we understand that it is very difficult to process this equation, right? If we are doing manual calculation, definitely we have tools where we can plug in the values and we can get the answers. But this equation itself is a very big expression, and we have considered only two stages. But we know that in RF transceiver chain, there will be lot many stages there, right? So there will be a lot of stages even after this. It can be up to 10 stages, 12 stages, many number of stages is possible. So then if you look for the noise figure calculation of that entire stage, this will become really difficult, or this expression itself is not easy to calculate, or this expression is not that easy expression. So what we will do now is we will modify this, or we will tune this expression so that even if you want to consider for many number of stages, I should be able to use a simple use in a very simple form. For that, I request you to closely look at the expression, and can you tell me what is this first term? First two terms. So now there are three terms. One is 1. The second term is Vn square divided by 1 factor, and the third term is Vn2 square divided by a huge factor. By closely observing this expression, are you guys getting what are these two terms? The first two terms.
I didn't understand the question, sir.
All right. The question is, there are
Noise
three
figure.
terms in this noise figure. Yes, somebody else is answering. Mahesh. Yes.
The noise figure is the third stage.
Yes, Mahesh. Yes, yes. So who asked the question? You didn't understand my question. Who is that?
I didn't understand the question, sir.
Rakshak. Yeah, the question is, you can see I have written the expression for the noise figure of two stages, and there are three terms in this. So this is first term. So this is first term, this is second term, and this is third term. So what I asked is, can you identify what is this for the first two terms? If you look at first two terms, we will understand that the first two terms is the way how we represent the noise figure of first stage or the single stage. Yes. All right. I hope Rakshak you understood that. So this can be represented as noise figure of first stage. Now I am making an effort to find the noise figure of second stage and write the third term. So I want to write this third term in terms of NF2. But I know that this is not only NF2, there are some other terms, extra terms are there. So anyway, let me find what is the noise figure of the second stage by considering only second stage. Are you guys getting what I'm trying to do here? Considering only second stage. Considering only second stage, that means I am taking only this gain stage of AV2. Right. So as Sagar, as you asked, for this stage, the RS will be the R out one of the previous stage. I am assuming that here you have some signal. This is V in, and this is R in 2, and this is Vn2 square, and this is V out, and from here what I have is R out 1. Right, this is second stage. Now I am writing the expression for noise figure of second stage. So how can I write NF2 in this case? NF2 can be written as 1 plus the noise component Vn2 square bar divided by what is the gain, total gain? 1 is R in 2 divided by R in 2 plus R out 1, the whole square, multiplied by AV2 square, right, into 1 by 4 kT RS, that becomes 1 by 4 kT R out 1. So this is the noise figure of second stage alone, right. Now what I'm going to do now is I'll check for the terms here in this expression. So in this expression, I wanted to write this expression in terms of NF2. So by looking at the NF2 of the second stage alone, I'll plug in this expression here, and I'll only write the remaining terms now. So I will take the same expression again, and here I know that 1 plus Vn2 square, this term. So this entire term is actually NF2. So I can write here as NF2 minus 1 can be written as Vn2 square bar divided by this term R in 2 divided by R in 2 plus R out 1. All right, third term is NF2 minus 1, Nikhil. Yes, I saw that. And Anirudh, but it is further attenuated. Which one is further attenuated?
Sir, it was actually in continuation to the previous message I sent.
So it is the second term. The second term in that expression is the noise figure of the second stage alone, but it is further attenuated by some factor.
I didn't get. Can you repeat? Anirudh? Are you asking a question to me or?
No, sir. I was actually answering the question you had asked
Oh,
to
all right.
identify what
Okay.
the second term
Okay.
is.
Okay. Okay. Thank you. Thank you then. So R into by R into plus R out square into AV square into 1 by 4 KT R out 1, right. So what I'm going to do now is, by picking all these terms here, I'll replace these terms with NF2 minus 1. So that I'll do here. So VN2 square I can erase, and what other terms I have, Rn2 term is there. So this the entire term can be removed. This AV2 can be removed, and I can write to the top, this is NF2 minus 1, provided it should be 1 by 4 KT R out 1, but R out 1 is not there. That means I should add actually R out 1 there, right? Is this correct? Or I will write R out 1 in the denominator itself. So this is 1 by R out 1. Or if I write this in a better way, this is NF2 minus 1 divided by R in 1 divided by R in 1 plus Rs the whole square into AV1 square. Oh, even 4 KT is there in the previous expression, right? 4 KT is also there, only R out is not there. So this term is not there. I need to add only Rs divided by R out 1, right? So I can represent noise figure, the total noise figure, as this. Or if I can write this as NF1, this is NF1 plus this term. NF1 plus this term, NF2 minus 1 divided by R in 1 divided by R in 1 plus Rs the whole square into AV1 square into Rs by R out 1, right. So this is so when you compare with the previous expression, this is a little more compact. Now one more thing I can find here. So if you look at the denominator term of this expression, so I can represent this denominator term, which is R in 1 by R in 1 plus Rs the whole square into AV1 square into Rs by R out 1. If you calculate, we will understand that this, the denominator term, is actually the available power gain of first stage. So the available power gain of first stage can be represented as say AP. Since it is first stage, I'll represent it as AP1. That means I can write this NF total as NF1 plus NF2 minus 1 divided by AP1. We will see how the denominator term is power gain. We will do that derivation shortly. But that is, we can consider that as the available power gain, and that can be marked as AP1. If that is the case, this will be your noise figure expression for your 2 stages. Now, if I want to extend this to say some many number of stages, for example, for m stages, I want to write this expression. I can write the NF total as, so the general way is to write it as 1 plus NF1 minus 1, right? So all terms we will write in this form. So 1 plus NF1 minus 1 is NF1 itself plus NF2 minus 1 divided by AP1. So one more, if you want to write, it is NF3 minus 1 divided by previous 2 stages power gain. So AP1 into AP2 plus etc. plus if you want to write the noise figure till m stages, it is nfm minus 1 divided by ap1 into ap2 into up to the previous power gain, the previous stages power gain. So ap of m minus 1. So this will be your total noise figure if you write the expression of noise figure up to some m stages. And this is very commonly called as Friis equation. I think you will see a similar equation even in your microwave class also. This is often called as Friis equation. And if you look at this expression, we understand that the noise contributed by each stage decreases as the total gain preceding the stage increases, right? So if you have a high gain stage in the initial blocks, the total noise figure contributed by the stages will actually keep on reducing, right? So the noise contributed by each stage decreases as total gain preceding the stage increases. Right. So this is how we generally represent noise figure up to many number of stages. Rakshak, I'm just reading your this one. NF1 plus NF2 divided by. Rakshak, you are answering to the previous calculations. Okay. All right. Okay. Yeah. Fine. So I hope this is clear for you guys. Noise figure calculation for 2 stages. So we'll come back to the power gain expression after solving one numerical on this. Let me give you one simple calculation. Now one more thing. So now we obtain the noise figure in very simple terms by whatever this Friis formula or this expression, right? If you know the individual noise figure of the stages and if you know the power gain of individual stages, then this formula turns out to be very easy. But that doesn't mean that that will be always easy. Now if the power gain is not available or the noise figure of individual stages, if it is not available, and if we know the noise figure contribution of individual stages as vn1 vn2, if you know rn1 rn2 rs etc., better to use this formula. So for that one example we'll take of a cascaded amplifier stage, and from that we'll get to know how under what circumstance we can use the Friis formula, or we can directly use the formula what we obtained before. So I'm just leaving a question here. So determine the noise figure of cascade of 2 common source stages. Assume lambda not equal to 0. So this is V in, this is RS, this is DC current source, this is the first stage. From the output of first stage, it is connected to again the MOSFET, connected to a common supply. This is, say, this is I2, and this is V out, and this is VDD. So this is M1 and this is M2. So assume lambda is not equal to 0. Find the noise figure, or do the noise figure calculation for this. So can I get a response from you guys? So in order to work out this, which formula is easy? Whether can we directly use the Friis formula, or we can use the direct expression what we have written first?
We can go with the Friis formula.
Okay, if you go with the Frisk formula, you should know the noise figure of individual stage first, and you should also know the power gain. But both things are unknown, right?
Yes.
Yeah. So in that case, direct.
So we need the how is the power gain different?
Yeah. So I'll do. You are asking for this AP, right? What is this AP? Okay. Now, yeah, the good
Yes, sir.
question. So power gain will be different than the voltage gain when the impedances are not equal, right? So we can consider the power gain same as voltage gain only when the input and output impedances are equal. So in this case, we have considered R in, RS, R in 1, R in 2, all those things, and it can be equal or it may not be equal. So if it is equal, both will be same. Otherwise, we need to consider separately.
So we need to add alpha to our gain.
I didn't get that.
Like we also had alpha, the attenuation factor for the
Yeah, yes. So
due to
attenuation
the
factor, yeah,
input
that we
impedance.
all, you're right, that we already included in the gain expression. If you remember, we have actually added the attenuation factor here. These two are the attenuation factors, right?
Yes, sir.
Yes, that is already included. What I'm telling is power gain. So why we need to calculate power gain separately is when the impedances are not equal, then voltage gain and power gain will be definitely different, right? Siddharth,
Yes, sir.
you understood that or
No, no, sir. Like, could you like just show in the previous example why we didn't need the power gain?
which example?
Like in the previous one, like in the chain demonstration,
Okay,
like or what element is power gain in that expression?
I didn't
Yeah,
get.
in this one,
Okay, here.
in
Yeah.
this, yeah.
Okay, so this one only I have written here, right? I have written in this form, and I included NF2 minus 1 also. This denominator term, you can see this denominator term,
Yes,
right?
sir.
But this I have marked as power gain, AP1.
Okay, sir.
Okay, so this is AP1, yes. Yeah, Rakshit, I am just reading your answers. First formula, but we need to first calculate enough power gain for CS. We can find AV square. Yes, that we can do, but that will take you actually, that is a longer step, I would say. You can directly, you can use a direct expression and you can substitute, because we know that for this particular example of this two common source stages in cascade, let me ask you, what is R in 1 in this case? What is R in 1? The impedance seen to the input of this R in 1 is infinity.
Infinite.
Infinity.
Yes, R in 1 is infinity. What about R in 2? R in 2 is also infinity. What is AV1? AV1 is a gain of the first stage, the individual gain of first stage. Yeah, it is GM1 into minus GM1 into R01. AV2 is minus GM2 into R02. And what else we know? We want R out 1 also. What is R out 1?
R
Yes.
naught one.
Yeah, R out 1 is R naught 1 of first stage. So R out 1 is R naught 1 of first stage. So we know all these things. And we also know the noise. Okay, I'll give you 2 minutes time. You guys can work out and let me know. I'll ask for the solution and then you can just let me know the answer. So others can also think. All right, so you got answers. Okay, Akshay, I am seeing your question now. How it is infinity? It will be
Sir, R into.
R in 2. Okay.
It's at gate of M2, right?
Yeah, the gate of M2. Yes.
Then it will be infinite parallel to R01, right?
No, I am looking into the gate of M2, right? I am writing what is R in 2.
Okay.
Yeah, the output impedance we already considered here. R out 1 is already here. Yes, R out 1 is here. But R in 2 is infinity, right?
Yes, sir. That way it's
Yes. Okay, so probably you are working on this numerical. So I'll just write the NF total expression. The expression what we obtained before is 1 plus Vn1 square divided by R in 1 divided by R in 1 plus Rs the whole square into AV1 square into 1 by 4 KT Rs. This is for first stage, and for second stage I can write it as Vn2 square bar divided by R in 1 divided by R in 1 plus Rs the whole square into AV1 square into R in 2 divided by R in 2 plus R out 1 the whole square into AV2 square into 1 by 4 KT Rs. So in this you can just plug in the equations here. So what is Vn1 square? Let me write Vn1 square separately. So for a MOSFET, generally we write In1 square. So In1 square can be written as in saturation. We assume that this is in saturation. This can be written as 4 KT gamma into Gm1. Similarly, In2 square can be written as 4 KT gamma into Gm2. Now to write Vn1 square, I should multiply this with R0 1 square. So it can be written as In1 square into R0 1 square. Yeah, Rakshak, all right. Okay, R into is R0. So you can plug in this by substituting all these values there, and you will arrive at the final answer. Probably I can do for one more step. So it can be written as 1 plus 4 KT gamma into Gm1 into R0 1 square divided by Gm1 R0 1 into the whole square into 1 by 4 KT Rs plus 4 KT into gamma into Gm2 R02 square divided by Gm2 R02 the whole square into Gm1 R01 the whole square into 1 by 4 KT Rs. So this will be the noise figure, right? So whatever infinity terms were there, I just neglected that and I plugged in all the other expressions. So if you further simplify this, you will get the answer as 1 plus gamma by Gm1 into Rs, because the other terms will get cancelled from the second term, and your third term will be gamma divided by Gm2 into Rs into Gm1 square into R0 1 square. Gm2 into Rs into Gm1 square into R0 1 square.
Sir, could you just point out the power gain part in this? Like we had AP in the formula, so like which component is that?
Oh, that is what. See, this was the expression what we have written, and from this we have we have written this NF2 form, NF2 into this, right? NF2 minus 1, and finally we arrived at this
Yes.
formula. So here you can actually see the power gain, or the power gain is basically this denominator term. But what I did here is I have taken the original formula, the direct expression, what is directly here.
Uh-huh.
Right. I have taken this. I have not taken the NF2 formula where you can explicitly see the power gain component. This is what I
Okay.
have taken. And on this formula, I have actually substituted all these values and put Vn1 square and Vn2 square and arrived at this and got the final expression.
Okay, sir.
Yeah, so it is easy, or I think the best way to find noise figure for these kind of circuit level things will be based on this. If you, because we know Vn1 square separately, and we can find the individual stages. But for the other thing, if you have given a number of stages without giving any circuit level details, then it will be easy if your noise figure and power gain expressions are given. Yes, Akshay. By seeing a MOS final expression, can to extend it to 3 stages. Okay, that is a good idea. GM1. Okay, for the for this kind of circuit. So, for example, if you have you have all the stage. If there is one more stage with an ideal current source in as the load with the lambda not equal to 0, yes, probably you can expand this. I don't know. I haven't tried that. It may be probably as you are thinking. I am also thinking it will be gamma by GM3 RS into the previous stage gains. I do not know. We have to check it. All right. Yeah. But for that, first we should write the expression, the direct expression for 3 stages, and we need to work it out. Yes. So with this, I will wind up for today's class. If you have questions, I can take questions now.